All right, this video is to help you understand inverses. That's what we're going to cover today is inverse functions. It says an inverse relation will undo a given relation. Every inverse relation can be found by switching each x and y value. So that's how we find the inverse. We switch the input and output variables. In some situations, this process is intuitive, but other times this may not be as obvious. In these cases, it is important that we understand the concept of inverse relations as they will help us tackle a variety of problems. Let's look at this numerically with tables, graphically with pictures, and analytically with equations. And we're going to start with the easier one, which is numerical. So for tables, when we are finding an inverse relation, again, we are switching that x and y, switching the input and output. So if this is my table for the y, original equation, then my inverse table, we would have these y values as our x values, and these x values as our y values. So we are switching that x and y value. It says the original table is a function because each input, which again is the x values, has exactly one output, which is our y values. However, the inverse is not a function because the x value, 2, has two different y values or outputs. And so what it's saying here is 1 has a unique y value, 3 has a unique y value, 4 has a unique one, and 6 does too. But when we go to this table, we look at the 2's and they do not have a unique y value. They have two separate ones. And so this is not a function. This one is a function. In order for it to be a function, every input has to have exactly one output. All right, let's look at it from a graphical standpoint now. We want to sketch the inverse relation of this. And so it tells us on the side to list the key points in a table, create a new table for the inverse by switching the x and y values, and then plot the new points for the inverse and sketch the inverse graph. And so we would want to create a table for our original points. And so we've got a point at -2, -1, -1, 2, 2, 1, and 4, 3. So I've taken these main points right here are the ones that I've put into the table, this one right here. And so now we're going to write the inverse table. And just to let you know that the inverse, we note that with this little -1 on top, that stands for inverse. So this would be the inverse of this equation right here. And so we said we do that by switching my x and y values. So my new x values are going to be these y values, and my new y values are going to be these. -2, -1, 2, and 4. Now we're going to go ahead and graph those points. And so -1, -2 is right here. 2, -1. Then we have a point at 1, 2. And then 3, 4. I did go ahead and put these in order as I work the table because it allows me to graph easier. So you do want to keep that in order. And so now we see the inverse function. So I'm going to go ahead and label this one here as f of x, and this is f inverse of x. So that's where that -1 comes into play. That is just the way we label inverse functions. On the bottom here, we've got a question. It says, is the original relation a function, and is the inverse relation a function? In Algebra 1, you heard about the vertical line test, where you can drop a vertical line anywhere and see if it hits in more than one place. If it does not, then it is an inverse. I'm sorry, it is a function. So that's what we can do here. If we look at the original, we can drop a vertical line anywhere, and it does pass the vertical line test. Again, that just means that every one of these inputs has exactly one output. Now, When we look at that, every input had one output. It passed the vertical line test. So is the original function? Yes, it is. Every input has one output. All right, is the inverse relation a function? Well, this one, no, it's not. If I dropped a vertical line right here, it would hit in 3 places. So this x value right here has 3 different output values. It's not one of the numbers on our table here, but looking at the entire graph, it fails that vertical line test right here. This input has 3 outputs. So the inverse is not a function. And I can say every input does not have a unique output. All right. So graphical property of inverse. The graphs and inverses are reflections over the line y equals x. And so if you remember that, that's one of your parent functions. But it's the point that goes right through the origin. I'm going to go ahead and graph it so you can see that it is a reflection. There's my y equals x line right here. I'll go ahead and label it. And if I folded it right there on that y equals x, then this part would be a reflection over this one, and this side would reflect over this one. So that too shows you if they are inverses or not, if it is a reflection across the y equals x line. All right, off to the back here. It says on example 3, find the inverse for f of x equals 3x minus 7. And we're going to look at this analytically now from the equation. And so for graphing, it told you to make a table of values and switch the x and y. For equations, it tells you to switch the x and y values, solve for y, which means get it by itself. And then if the original equation was an f of x form, write the inverse equation as f of negative 1x. All right, so there's a quick reminder, f of x and y are interchangeable. They're both a function dependent on x. So my first step here is I'm going to go ahead and rewrite that as y equals 3x minus 7 so that I have the x and y to switch. Now we switch that x and y. In math, though, we never leave the dependent variable inside the equation, so we want to solve for this y. So I'm going to bring the negative 7 to the other side of the equal sign, and we do that by adding 7. And then we divide by 3 because these two are being multiplied. And so we get y equals x plus 7 over 3. And so now we're going to label it correctly, which is with the little negative 1 there. And so my final answer should be written with that inverse notation. And so that would be x plus 7 over 3. All right. There's some steps there for helping you find some inverses that are a little bit more difficult. For example, rationals. So the steps are typed there for you. I'm not going to read through all of them. I'm going to go ahead and do a problem with you so that you can see it because these are a little bit harder to do. All right, our steps still the same. We're going to go ahead and write that with a y. Now we switch our x and our y. When we do that, we had 2 x's, now we have 2 y's. You do have to switch both of them. All right, this is set up as a proportion, so we can go ahead and cross multiply. And any whole numbers over 1, so that's x over 1. So now we're going to cross multiply, and we get y minus 2 equals x times y plus 3. If I distribute that, I get xy plus 3x. Now, I have a y here and a y here, so I'm going to get both of my y's to one side and the number to the other side. So we've got y minus xy, because I subtracted this to get it to the other side, and then I have 3x plus 2 because I added that 2 to get it to the other side. The reason why I did that is because now my y's are on one side, and I need to get them by themselves. In order to do that, we factor. Everybody's favorite. And so when we factor, we're undoing the distribution. Y times 1 would be this, and y times negative x would give me this here. And so the reason why I factored is because now these two are being multiplied, so I can actually bring this to the other side by dividing. And so y equals 3x plus 2 over 1 minus x. And my final answer should have the proper notation. And so I'm going to go ahead and change that so that my notation is written correctly. All right, if you'd like to pause it and try it yourself, you can go ahead and do that on this one and then check your answer, but I will go ahead and do a second one because that was a little bit of a doozy there. All right, so step 1, I'm going to switch my x's and my y's. Now I cross multiply, and so that's over 1, so 2y plus 1 times 1 is 2y plus 1. When I multiply here, I get xy minus 3x. I'm going to get the y's on one side, everything else on the other side. So I get 2y minus xy equals negative 3x minus 1. I subtracted this 1 to get it to the other side, and I subtracted that xy to get it to the other side. Now I can factor that y out. And when I factor it out, it shouldn't be there anymore. So y times 2 gives me 2y, and then times a negative x there. Now I divide by 2 minus x. And so we get y is equal to negative 3x minus 1 over 2 minus x. And so my inverse notation is right there. All right, we're going to continue to go a little bit deeper with inverses, and we'll go back to the graphing a little bit. It says we know that to find an inverse, we can simply switch the x and y values, and that graphically this means that a function and its inverse will be a reflection across that y equals x line. That's what we talked about a little bit earlier. There is a little bit of a different way of sketching it. This may or may not help you. It says sketch the line of y equals x, since we know it's going to be a reflection. Mark the points that are on that line, and then select a few additional points on the original graph and find their inverse points. You can find the inverse points by switching the x and y values, or graphically reflecting each point over the y equals x line by drawing a line that is perpendicular. So we're going to look at that a little bit here. We're going to try and find the inverses for these two graphs here and to sketch the graph. So it tells us here to go ahead and graph the y equals x line. So I'm going to do that first here. There's my y equals x line. Since it's a reflection over this point, the ones that are on that line are going to remain on that line, because you can't really reflect it if it's on that line. So you can start with those points right there and then choose a few more. Like this point right here is at 2, 0. And so if I flip that, then that goes to 0, 2. I had another nice point right here at 3, 1. And so I can change that to 1, 3. Remember, we're switching that x and that y value. We had another good point right here at 0, 4. And so if I switch that x and y value, that's going to give me that point at 4, 0. And I think I have enough there to sketch my picture. And so there would be the graph for the inverse. The ones that are on the y equals x line are still there. And then I used my new points to go ahead and sketch that picture. All right, we'll do that again for this one here. If it is on the line, again, those are still going to stay as points on my graph. Now we start to switch a few points that we can find. We've got one right here at 1, 0. So if I change that, that's going to go to 0, 1. Now in between there, 1/2, I got like a negative 1/2. So negative 1/2, 1/2 is also going to be on my graph there. I think that's a good one to get. So I keep looking for a few more points. I've got another point here at -2, 0. So 0, -2 would be a point. I'm going to go ahead and get this one too, right here at negative like 1.25 and a little over 2. So a little over 2 and negative 1.25. So that's about right there. That kind of gives me a picture of what my graph is going to look like. And so it's going to come this way. And there it is. You can notice that it's a reflection across that y equals x line. You can do the points, switching them. So whatever makes it easier for you to be able to graph that inverse. All right. If you plug a number into a function, it generally will output a new different number. For example, if we plug x equals 2 and the function f of x equals 3x minus 1, we get 5. Now, if we plug the answer into the inverse function, the answer should be 2. In other words, if this is my input, and that's my output, in the inverse, this is going to be my input, this is going to be my output. You are switching that x and y, the input and output values. This is because an inverse function essentially will undo a function. So if we plug x into a function and then plug the output into the inverse function, we should end up with x again. All right, so to continue with these inverse functions, last time we learned about compositions. Well, part of the definition here with inverses is that two functions, if f and g of x are both inverses of each other, then if we did the composition of that, it would answer x. And that would be in both directions. So if g of x was the input and if f of x was the input, you would end up with x. To show that the functions are inverses, we must show that the inverse of f of x and f of the inverse both equal x. So you do have to show it in both directions. So we're going to do that example here. The first step would be to find f of g of x, and the second would be to find g of f of x. So first we'll start with this one. G of x is going into f of x, so I'm going to take this whole thing and I'm going to replace this x with it. And so we get 2, 1/2 x plus 3 over 2. I distribute my 2 all the way in there. And so 2 times 1/2 is just 1, and 2 times 3/2 is just 3. And so we get x plus 3. Oh, I had forgotten the minus 3 there. And then minus 3. So this was 2x minus 3 from this equation right here, 2x minus 3. I then distributed the 2 into my new equation, got x plus 3, and then we have a minus 3. Plus 3 minus 3 is 0, and so this came out to be x. All right, now we're going to try it the other way, and so f of x is going to be my inside function, and g of x is going to be my outside function. So this is my outside, so I get 1/2 my new x, which is 2x minus 3, plus 3 over 2. I distribute. 1/2 times 2x is just an x, because 1/2 times 2 is 1. 1/2 times -3 gives me a -3 over 2 plus 3 over 2. And then -3 over 2 plus 3 over 2 is 0, and so we end up with x. Some of you guys like to skip a bunch of steps, and you'll just cross everything out here and just say x. That does not work. You do have to follow the order of operations to make sure that it comes out correctly. So the first step would be to distribute, and then to add these two together to get 0 and end up with x. So don't just go from this step to the last one, because you will lose points. All right. Sometimes we must use a restricted domain to ensure functions are inverses. So show that h of x and k of x below are inverses, where x is greater than or equal to 10. State the domain. So what it's telling you here is that this is a quadratic. Just off to the side, you know that a quadratic looks like this. This is a radical, and so you know that a radical looks like this. So this is not a reflection. You can tell this is not a reflection over the y equals x line. So this says when x is greater than 10. And so what it's doing is it's limiting to one side of the parabola so that you're able to find the inverse function, which would just be one side. So one side would reflect to the one side. All right. So in order to do that, we're going to go ahead and find our h of k of x here. And so I'm going to plug in my k of x, and I get the square root of x minus 10 squared plus 10. The square root and the square cancel, and so we get x minus 10 plus 10. And so that is 0 there when you add the negative 10 plus 10, so that is just x. Now again, you do have to do both sides to prove that is true. And so now I'm going to do it the other way around. And so I'm going to plug h of x into the k of x. And so we get x squared plus 10 minus 10. This one is especially important for those of you that try and cross everything out. You cannot cross the square root and the square out since we have the plus 10 minus 10. So the first step would be to add the 10 and the negative 10. And so that gives us this right here, square root of x squared. Now I can cross this out since it's the only thing in the square root. And so that gives us x. So these are inverses of each other. We've proved it right here. And so it gave us that the domain was greater than 10 to prove that it was only one side of the parabola. All right. Show that n of x and p of x below are inverses where x is x is unequal to 0 and x is unequal to 4. And so again, they've given us a domain restriction, and that is because if we plugged in 4 right here, that would give me a 0 in the denominator. And if I plugged in 0 here, it would give me a 0 in the denominator, which is undefined. So anytime that you see like these domain restrictions, they are there just to make sure that our finding the inverse is possible. All right, so go ahead and pause this one and try and find the composition to verify that it comes out to be square root of x. Not the square root of x, sorry, just x. So go ahead and do the compositions and verify to see if they are inverses by doing the composition and finding x. All right, check your work there. They did both come out to be x, so we know that they are inverses of each other. If it came out to be anything besides x, then they are not inverses of each other. So we've talked about how these are inverses because they both have come out to be x, but just so you understand, if you do the composition, it comes out to be anything else, then they are not inverses of each other. All right, this has been a big lesson, but we're almost through it. It says if f and g are inverses, then g of x is equal to f of inverse x. So if x and y, so these are really important points if you want to star this and make sure that you go back and look at it and make sure you understand everything in this chart. So if f and g are inverse functions, then g of x would be our main function, and this would denote inverse. Just make sure you understand that that means inverse. If x and y is a point on the graph of f of x, then yx is a point on the graph of g of x. So if they are inverses, then you can switch those x and y's. With inverse functions, all of the x and y values are switched, so the graphical behaviors in terms of x and y will also be switched. For example, the domain of f is the range of the inverse of f. So since we switch the input and output, the domain and the range also switched because the domain is the input and the range is the output. A continuous function will only have an inverse function if it is strictly increasing or strictly decreasing. If a function changes from increasing to decreasing or vice versa, it will not pass the horizontal line test, and its inverse relation will not pass the vertical line test as a result. And so that is just a little side note. We haven't really talked about the horizontal line test right here. It is very similar to the vertical line test, but it tests to see if the inverse will be a function. Not if it is a function, but if its inverse will be a function. So if we dropped a horizontal line and it touched in more than one place, then the inverse will not be a function. That's what that means. All right, so here is some examples on example 8. Let f be a continuous function with the selected values in the table below. Let g be the inverse of f, such that g of x is equal to f inverse of x. Find the following values if possible. So f of 0, well, we did this in compositions. This has nothing to do with inverses since we do not have a little -1 there. We do not have the g of x that we said was the inverse. So in this case, I would just have my input of 0 has an output of 1. And so this becomes f of 1. And so then I would go to the input of 1 and my output would be -1. We did that in the last lesson. This is the one that's an inverse. We said g of x is the inverse of this one. So if we are looking for the input in the inverse, then we are looking for the output in the other one. So I would come to the outputs here, and so this would be 4. Take a minute to let that sink in. If it is the input in the original, it is the output in the inverse. All right, so again, this is the inverse. And so it is asking for the input of the inverse, which would make it the output of the original. So I would go to the 6, and so that is -3. And so here's one that's pretty confusing because now we've got a composition with the inverses. So this is the inverse. If it makes it a little bit easier for you, you could write a new table with the g of x. And so in order to do that, you would take our output values and make them our input because we switch. And then our inputs would be our outputs. And that might make it a little bit easier for you. So that's always an option. So we're looking for g of -1. If I come here, this is -1. My g value is +1. And so this becomes g of 1. Then I go to 1 and my value there is 0. If you're going from this table, if it is the input for g, it is the output for y. So I would come here and it would be 1, which comes here. And then I'm looking for 1, and there's the output of 0. All right, so this says the f inverse of f of -2, and so I would start with -2 as my input for f. Well, this is f, so I'm going to the regular input. The output is 3, and so I'm looking for the inverse of 3. Now, this is the inverse, not the f, so now I'm looking for it as the output, and so that would be -2. And then my last one, the inverse of -3. So that's my output. And so that would be 4. That's tricky. You really have to think through those. All right, example 9, the function k is defined over the interval -4 to 11 as shown above. K inverse represents the inverse of k. What is the minimum value of f of x, and what is the minimum value of k inverse x? All right, so if we look at k of x, the minimum value is right here. That's my smallest y on the graph, which happens at -3. If I think about this inverse, the minimum value would be the input of k of x. Because remember, that switches. And so this is my k of x graph. And so I'm looking for the smallest x. Well, the smallest x would be this one right here at -4. That would become my smallest y values when it switches. All right, here's another way of thinking that on the graph. Find the inverse of k, 6. Since this is inverse, we're talking about the y value of k of x here. It's in the place of the X, but remember the inputs became the outputs on the inverse since you switched it. So I would go to 6. I'm going to write it out here on the Y. And my X value there is 11. And then the inverse of 4, so I'm going to go to my Y value of 4, and that is 6. So it doesn't say it here, but I am going to go show you. That means that K of 11 is 6. So this is the original function input is 6. See how they switched? And in the original function, K of 6 was 4. I'll let that sink in for a little bit. So here, input, output, and then that became my input, output when they switched for the inverse. All right, there's another one for you to try here. So if you want to pause it and try there, and then come back and look at those answers, they're very similar to the questions that we just did, with a little bit of a different graph. So go ahead and pause, try it, and see if you get it right. There you go. Those are the answers for that graph of F. And then we've got one more with compositions in 2 different functions here. It says the function of g is defined over the interval -3 to 10 as shown above. Let the inverse of g represent the inverse of g. Values of the increasing function h are given in the table above, selected values of x. Find the following if possible. So this is just a regular composition, g of h of 6. So h is my table, so I'm going to go to 6. Its output is 10. So this becomes g of 10. G is my graph, so I'm going to go to 10, and its value there is -1. That's from last time's lesson. This is the one that puts both of these lessons together. So we're going to start from the inside, h of 0. That's the regular graph, so I'm going to go to 0. My h of x has a value of 3. And so now we are looking for g's inverse at 3. That means that this is the y value of the g graph. So I'm going to go to 3 and my y value, and that is 4. All right, so g of 8, this is the regular g. This is my graph right here. So I'm going to go to 8. My graph there is at 0. So this becomes h inverse of 0. All right, so if we're looking for the inverse, this is the regular h of x. So if we're looking for the inverse, this would be the y value of 0. So here's the y value of 0. And so this would be -1. All right, and then this one, we're looking for the inverse of g at -1. So I'm looking for the y value, of -1, and that is 10. So that becomes the inverse of h at 10. And so if this is the inverse of h, I'm looking for the y value of 10, which is here. And so my final answer would be 6. That was a big lesson, lots of stuff. Remember, for inverses, switch that x and y. It does switch the domain and range. It switches the input and output. So you do have to think through all of that. It was a big lesson. Thanks for making it all the way through.